Another problem-solving question, as usual, and honestly, this is a really good question, not because it's easy or anything, but because it really does test if you understand what a geometric sequence is. So, just before we continue, a geometric sequence is one where you times by the same number every single time. So, for example, if I have the numbers 2, 4, 8, 16, 32 as a sequence, I'm timesing by 2 every single time. So that means this is indeed a geometric sequence. This is normally called the common ratio R. I know ratio sounds a bit strange, but if you think about what a ratio is, it's a proportion, and when you multiply by 2, it is a proportion to an extent. So the common ratio is simply the number that you times each term by in order to get the next term. So I do 2 times 2 is 4, times 2 again is 8, times 2 again is 16, and so on. So if I have a look at this, we have the first 5 terms of a geometric sequence. We have root 5, 10, 20 root 5, 200, 400 root 5. Work out the next term of the sequence. The only way to do this is to, well, okay, I say only way, but in my opinion the best way to do this is to work out what the common ratio is. Now, how could you work that out? Well, how did I work out the common ratio in this one? Well, I looked and said, well, 2 times what gives me 4? 4 times what gives me 8? But another way you can do it is to simply divide the terms, right? If I do 4 divided by 2, I get 2. If I do 8 divided by 4, I get 2. If I do 16 divided by 8, I get 2. So all you need to do is divide any 2 adjacent terms in order to get the common ratio. So I could do 32 divided by 16 also gives me 2. So that means 2 must be my common ratio. So if I do the same thing here, these 2 terms are... You can actually use any 2 terms, by the way, as long as they're next to each other. But I would probably pick the first 2 because the numbers are as small as possible, right? They get bigger as we go along. So if I do 10 divided by root 5, that is actually what I'm timesing by each time. Now, I don't really like this. I'm actually going to rationalize it. So I'm going to times top and bottom by root 5. So that gives me 10 root 5 over 5, because again, root 5 times root 5 is square root 25, which is just 5. So that means I'm timesing by 2 root 5 each time. So, and that makes sense, right? 10 times 2 root 5 would give me 20 root 5. And 200 times 2 root 5 would give me 400 root 5. The reason why I picked those terms is because I can clearly see it just by looking. Going from 20 root 5 to 200, it takes a bit more effort, right? 20 root 5 times 2 root 5 is 200. That's harder to spot. So if I want the next term, I need to do 400 root 5 times by 2 root 5. So 400 root 5 times 2 root 5. I'm going to start by doing the 400 times 2, which gives me 800. Root 5 times root 5, well, I actually did that already over here. That would be square root 25, which is 5. So now we have 800 times 5. I would then just do 8 times 5, which is 40, and then add on the 2 extra zeros. So the answer is 4,000. Okie dokie. Now, the fourth term of a different geometric sequence is 5 root 2 over 4, and the sixth term is 5 root 2 over 8. Given that the terms of the sequence are all positive, work out the first term of the sequence. Cool. This is going to be a bit trickier. Now, again, remember my golden rule. Well, it's 2 rules, really. They always give you enough information to complete the question, and they never give you extra information. So the fact that they've told me that this is the 4th and 6th term is actually relevant, because if I put it as a blank, we have term 1, term 2, term 3, term 4, blank, well, that's term 5, and then we have term 6. Okay, that's what my sequence look like. That's what it looked like. That's what it looks like. And I'm trying to work out the very first term in the sequence. So how can that work? Well, if I go back for a second, I mentioned that to find the common ratio, you can divide any adjacent terms. There is something else you can do, and this is a bit spicy. So I'm going to use this exact same example. So we have that 2, 4, 8, blah, blah, blah. As you can see, in this case, we do not have adjacent terms, but we do have a term next to a term. So to go from this term to the next one, I times by the common ratio R. And then to go to the next term, I times by the common ratio again. That's the same as timesing by the common ratio squared. Let me show you how this works. We know that going from here to here is timesing by 2, and going from here to here is going timesing by 2, right? But if I want to jump straight from here to here, I could times by 2 squared. I times by 4. I could do this with any, what am I trying to say? Any term in the series. So I could also go from 2 straight to 16 by timesing by 2 to the power of 3 instead, or 2 times 2 times 2, which is 8. Or I go from 2 to 16 by timesing by 2 to the power of 4. Okay? So if you want a general equation for a geometric sequence, it looks like this. AR to the power of n minus 1. A is your first term. N is what term you're looking for, and R is your common ratio. So if I want the third term, I'll take my first term and times it by R to the power of 3 minus 1, so R to the power of 2, R squared. So I can work out the common ratio in this question by dividing these two terms and then square rooting it. So R squared is equal to 5 root 2 over 8 divided by 5 root 2 over 4, good old-fashioned KFC, 5 root 2 over 8 times, so keep flip changed, keep the first fraction the same, we're going to flip the second fraction, and we're changing the divide to a times. Now, I personally really like cross-cancelling, so I can see that I can cross-cancel 5, I can cross-cancel root 2, and I could cancel this out to make that 1 and 2. So in other words, R squared is just a half. Cool. Now, that's R squared, which means R is equal to the square root of 1 over 2, which is just 1 over root 2. Again, I do personally like to rationalize denominators, not just like in general, just, you know, for questions. I'm not that weird. So that would be root 2 over 2. And that is my value for R. Perfect. Cool. So very similar to the first part, we've worked out the common ratio, but we had to do the square root thing. If they wanted to change that this year or next year or whenever you're watching this, they could easily make it, you know, the fourth term and the seventh term, in which case you'd have to cube root it. If they, you know, they can make it any, right? They could say the first and third term is something, what would the fifth term be? In which case you can do that kind of thing. But the idea is that you should be able to know, or be able to realize, be able to work out that you can jump places in a geometric sequence by just timesing by the ratio more than once. So if I jump and I skip one, I'm doing it by R squared. If I skip 2, it's R cubed, and so on. Now, it did say, given that all of them are positive, why did they tell me that? Well, there is something I neglected to mention. Technically, all of this is plus or minus, because when you square root something, it can be plus or minus. But if they're all positive, it means my ratio has to be positive. Because think about it, right? If I'm timesing by a positive number all the time, my sequence will always stay positive. If I'm timesing by a negative, it will flip between positive and negative answers. So the reason why we couldn't spot that straight from here is the fifth term could have been something like negative whatever, in which case we could have had a negative common ratio, and that's completely legal. It's completely legit. So they're just pointing out that every other term could have been negative, but in this case they're all positive because our common ratio is indeed positive. So how can we get back to the original term? Well, we can use a similar technique to this. There's a few ways. We could just keep dividing by the common ratio until we get back to the beginning. So I'd divide by, R, get the answer, then divide by R, get the answer, and then divide by R. Or I can divide by R cubed. So all we're going to do is we're going to take 5 root 2 over 4. I'm actually going to just do this on the side, I think. So 5 root 2 over 4, divide it by root 2 over 2 cubed. Is there any way I want to... Okay, we'll do it the usual way. So we divide, that'd be over 8. When we have root 2 times root 2 times root 2, if I write that out, let me show you what it looks like. Root 2 times root 2 is root 4. Root 4 is 2, so that becomes 2 root 2. Okay? Again, make sure you are able to follow along with this logic. So that becomes 2 root 2. I don't need the brackets anymore. Now we do keep flip change. So times, and it becomes 8 over 2. Same thing as usual, cancel out the root 2's. We can cancel that, make that 4. So that becomes 5 times 4 over 2. So in other words, it becomes, well, 4 over 2 is 2, it becomes 10. Wonderful. For 3 marks, I don't know how useful or good that is. Honestly, I don't think it's that great. But hopefully you can kind of see where that comes from. I'm just going to double check to make sure everything I've done is indeed correct. So 8, 4, yeah. So very interesting question, very tricky as well. Hopefully you can kind of see where each of these individual pieces comes from. And again, with geometric sequences, a lot of people know geometric sequences and maybe they'll be able to do part A. But in my opinion, it's one of the weak parts for students. And part B, very few people will be able to do it. There's a lot of stuff you need to know in GCSE maths. Geometric sequences doesn't come up too much, but it's coming up before. It's come up before. So do make sure you understand it. Remember, it's not just about memorizing stuff, it's about understanding why we're doing it. That's how you learn. So, see you in the next one. Just before we go on, I do notice that that should actually be a 2, which means that should be 5 times 2 over 2, which is 5, not 10. That's my bad. For some reason, I thought 8 divided by 4 was 4. That makes a lot of sense, doesn't it? But hopefully that didn't confuse you too much, and I will now see you in the next one.